Hi everyone and welcome to this presentation. It's all about the different sorting techniques. By the way, I am your DELA GRACIA and let's start the first method.
1. Bubble sort. It's the simplest sorting algorithm. Then word by repeatedly swapping the adjacent elements. They are in the wrong order. For example, how bubble sort works. Point 1. Start with the first two elements in the list. 2. Compare them. If the first element is larger than the second, swap them. 3. Move to the next pair of elements and repeat the comparison and swap if needed. 4. Continue this process. For the entire list. 5. Repeat the whole process. For all elements, ignoring the last element after each iteration, as it's already in the correct place.
Sure. We have a 4, 3, 5, 1, and 2. I-compare natin yung 4 sa 3. Mas less than ba ang 4 sa 3? No. Kaya, iswap natin yan. Sulat natin ulit. 3, 4, 5, 1, 2. Compare naman natin yung 4 sa 5. Mas less than ba ang 4 sa 5? Yes. Kaya, isulat natin ulit. 3, 4, 5, 1, 2. I-compare naman natin yung 5 sa 1. Mas less than ba ang 5 sa 1? No. Kaya, swap na natin. Swap natin yung 1 sa 5. 3, 4, 1, 5, and 2. I-compare naman natin yung 2 sa 2, yung 5 sa 2. Mas less than ba ang 5 sa 2? Yes. No. Mas less than. Kaya, i-compare na natin yan. Sulat natin ulit. 3, 4, 1, 2, and 5. Nasa tamang order ba ang 5? Yes. Kaya, ganyan natin. Kasi nasa tamang order na yung 5. And compare na, iulit naman natin ang swapping mula sa umpisa. I-compare naman natin yung 3 sa 4. Mas less than ba ang 3 sa 4? Yes, kaya isulat natin dito 3, 4, 1, 2, 5. I-compare naman yung 4 sa 1. Mas less than ba ang 4 sa 1? No. Kaya i-compare natin yan. Ay, iswap natin yan. Sulat natin ulit. 3, 1, 4, 2, 5. Compare naman natin si 4 sa 2. Mas less than ba ang 4 sa 2? No. Kaya, swap natin yan. Swap natin yung 4 sa 2. We have 3, 1, 2, 4, 5. Compare naman natin si 4 sa 5. Mas less than ba ang 4 sa 5? No. Kaya, dyan ang tamang order si 4. Kaya, lagyan natin ito. Kasi nasa tamang order na siya. Then, we have 3, 1, 2, 4, and 5. Balik na naman tayo sa umpisa. Mag-swap naman tayo sa pinakauna. I-compare naman natin ng 3 sa 1. Mas less than ba ang 3 sa 1? No. KHEY. Para lang daw buang ko. Kaya iswap natin yung 1 dito sa 3. We have 1, 3, 2, 4, and 5. I-compare naman natin si 3 sa 2. Mas less than ba si 3 sa 2? No, kaya iswap natin yan. Kaya swap natin ang 2 sa 3. We have 1, 2, 3, 4, and 5. Compare naman natin si 3 sa 4. Mas less than ba ang 3 sa 4? Yes, kaya dyan ang tamang lugar niya. Nasa tamang order na ba sila? Okay, dahil nasa tamang order na sila, dyan tayo mag-e-end. Yan ang example ng bubble sort. Oh yeah! Let's count the swapping. We have 1, 2, 3, 4, 5, 6, 7. I have 7 swapping.
Two, selection sort. Selection sort is a simple sorting algorithm that repeatedly selects the smallest or largest dot element from the unsorted part of the array and moves it to the sorted part. Here's an example to demonstrate how it works. Steps of selection sort: dot 1. Find the smallest element dot in the unsorted portion of the array dot 2. Swap it with the first element of the unsorted portion dot 3. Move the boundary between the sorted and unsorted portions one step to the right dot 4. Repeat until the entire array is sorted dot.
And this is the example. Maglagay tayo ng number. We have 5, 7, 6, 4, 8, and 30. We have 6 numbers. Okay, sa ating selection sort, ang first step natin is hanapin natin yung pinaka-smallest na number. Bilugan natin yon at iswap natin with the less element. Ilagay natin sa unahan. Iswap natin doon. Then nakita na natin, sulat ulit natin. We have 3, 5, 7, 6, 4, and 8. And then, pagkatapos nun, hanapin naman ulit natin yung smallest element maliban sa 3 kasi nasa correct position na siya. Nung nahanap na natin yung smallest element, bilugan na ulit natin ito at iswap naman natin sa second element. Ilagay natin siya sa second. Yan. Then, sulat naman natin 3, 4, 5, 7, 6, and 8. And then, hanapin naman natin yung ikatatlong smallest. We have 5. Bilugan natin ito. Dahil nasa correct position na siya, hindi na natin yan gagalawin. Isulat na lang natin ulit. And then, hanapin naman natin ang smallest. And then, wait, nagay natin ulit. We have 3, 4, 5, 7, 6, 8. And then, hanapin natin yung smallest. We have 6. At ilalagay natin dito sa fourth element. Nasa gitna ng 5 and 7. And then, isulat natin yung ulit. We have 3, 4, 5, 6, 7, and 8. And then, hanapin naman natin yung smallest. Ang smallest na nakita natin, we have 7. Bilugan natin ito. And then, hindi na natin gagalawin yan kasi nasa correct position na siya. And, I think, nasa correct position na ang lahat. Ito, lahat. And, yan ang example ng selection sort.
3. Insertion sort. Insertion sort is a simple sorting algorithm that builds the sorted list one element at a time by inserting each element into its correct position. For example, steps: dot 1. Start with the second element, index 1, compare it with the elements to its left, and insert it in the correct position dot 2. Repeat this process for all elements in the array.
For example, we have a 5, we have a 3, we have a 8, We have a 6 and we have a 2. Then, compare to si 5 sa 3. Less than ba ang 5 sa 3? Of course, hindi. Kaya, i-insert ko siya sa unahan ng 5. Hindi sa 5, kundi sa unahan ng 5. Ha? Nag-bal ni ma'am. Then, sulat naman, we have a 3, we have a 5, we have a 8, we have a 6, and we have a 2. Then, compare naman natin si 5 kay si 8. Mas less than ba si 5 sa kay 8? Yes, kaya stable lang na siya dara. Then, compare na naman natin. Let's move naman daw kay 8 kay si 6. Compare naman natin siya. Mas less than ba si 8 kay 6? Hindi, kaya ibutan ta siya sa unahan sang 8. Kailangan sa unahan sang 5, kaya mas less than si 5 kaysa kay 6, kaya diri siya sa tunga sang 5 kag 8. Kaya less than siya kay 5, tapos greater than siya kay 5 and less than siya kay 8. Okay? Okay. Sulat na tayo 3, 5, 6, 8, and 2. Yun naman, si 8, i-compare na naman natin daw siya kay 2. Si 8 pa is less than kay 2? Alright. Dahil less than si 8 kay 2, i-insert siya kay 2. Din tayo i-insert sa 2. Sa unahan ba sang 8? Kay greater than si 6 kay 2, so unahan pa daw. Kay greater than man si 5, so unahan man. Kay greater than man si 3 kay 2, kaya sa unahan siya ni 3. Okay? Over 2, 3, 5, 6, and 8. Okay. Nasa tama na ba siya na lugar? O nasa tama siya? And then, bilangon ta kung pila ta nag-insert. We have a 1, we have a 2, and we have a 3. 3 insertion. We have a 3 insert. Okay? Okay.
4. Merge sort. Merge sort is a divide-and-conquer sorting algorithm that splits an array into smaller subarrays, sorts them, and then merges them back together in sorted order. For example, how it works: 1, divide, split the array into two halves until each subarray contains only one element, 2, conquer, sort and merge the subarrays into larger sorted subarrays, 3, combine, continue merging until the entire array is sorted. For example,
I-divide ko daw siya sa 2. Divide siya sa 2. Then, sabi daw ni mom, mas mataas daw dito. So, 28, 22, and 20. Mas taas daw dito, ay mas matimbang daw dito kaysa dito. Kaya dito ibutan natin si 19 and si 10. And then, divide naman natin siya dito. I-divide natin ang dito. We have 28, 22, and dito ang 20. Mas matimbang pa rin sa left, kaya and then naman, i-divide naman natin dito si 28 and 22. Divide sa 28, 22. And divide lang. And dito is dapat balance daw, kaya dito divide, kaya i-bring down na natin. Wala tayong i-divide sa 20, kaya i-bring down na natin yung 20. Dito naman sa kabila, i-divide naman natin yung 19. We have a 19 and 10. Kaya merge siya, kailangan i-balance, kaya i-bring down naman natin ang 19 dito. Then, i-bring down din natin ang 10. Kaya dapat naka-balance. Dito, tawag dito is divide. Dito, kasi divide natin sa dalawa. Dito rin, divide. Kasi, divide natin dito at dito. Then, dito, divide. Kasi, divide rin natin dito at dito. Tapos sa divide, may tinatawag tayo sa merge na conquer. Dalawa yon kasi divide at conquer. I-conquer naman natin ang sa kabila, unahin natin dito. I-conquer natin ang 28 at 22. Conquer natin, balik. Pero pag conquer, dapat na sa tamang pwesto na. Dapat si 22 nandito kasi siya ang less than sa 28. Then ang 28, ilagay mo dito. Conquer na siya. Then, walang i-conquer ang 20, kaya bring down na natin ang 20. Bring down. Dito naman, i-conquer naman natin ang 19 kat 10. Dahil mas less than si 10 kay 19, ilagay natin sa unahan si 10 at ilagay natin sa huli si 19. Then dito, i-conquer naman natin dito si 22, 28 at 20. I-conquer naman natin siya. Dahil mas maliit si 20, ilagay natin sa unahan. Then, isunod natin si 22 at si 28 ang last. Dito na part, walang i-conquer ang 10, kaya ang 10 at 19, kaya i-bring down lang natin. Bring down natin yung para balance sila. At ngayon, nasa baba na tayo. I-conquer naman natin ang dalawang grupo. Ito. At kailangan natin ilagay sa tama na order. Kaya, unahin natin si 10 kasi siya ang less than sa lahat. Si 10, susunod natin si 19, sunod natin si 20, sunod si 22, at sunod naman natin ay si 28 ang last. Kasi siya yung pinaka malaki. Siya yung greater than sa lahat. Lagyan na natin ng conquer. Dahil dito, gin-conquer natin siya. Gin-conquer. Then, gin-conquer natin sa kabila. Kaya, balance sila. Kasi, conquer sa lahat. Kaya, dito na side is tinatawag natin na conquer. Dito rin, i-conquer natin. Dito, i-conquer din natin. Kaya, conquer. Balance sila. Then, dito naman is i-conquer natin. Conquer naman natin. Ito ang example ng merge sort.
5. Quick sort. Quick sort is a divide and conquer sorting algorithm that organizes elements in an array based on a pivot. How it works: 1. Choose a pivot. Select a pivot. Element from the array ... 2 partition. Rearrange the array so that : 3. Elements less than the pivot dot are on its left ... 4. Elements greater than the pivot are on its right.
We have 8, 3, 1, 7, 0, 10, and 10. So, quick sort, dito sila naghahanap ng pivot. Ang ating pivot ay naghahanap sila ng pivot sa last na number. Kaya, ang last na number natin ay si 2. siya ang ating pivot. Dahil siya ang ating pivot, hahanapin natin yung less than, ang element na less than sa 2. Ang element na less than sa 2 ay C1 at C0. Ang element na less than kay 2 ay C1 at C0. Ang element naman, hanapin naman natin ang element na greater than kay 2. Ang element na greater than kay 2 ay C8, C3, C7, at C10. At i-arrange naman natin ito sa correct answer. Ilagay natin dito ang element na less than kay 2. We have a 0, 1 and 0. Then, ilagay natin si 2 sa gitna. Then, ilagay naman natin sa left side ni 2 ang greater than sa kanya. C8, C3, C7, at C10. Next, dahil nasa tamang lugar na si 2, ilagay natin si 2 dyan. Kasi nasa tamang order na siya. Next naman, hanapin naman natin yung pivot. Ang ating pivot naman is, mauna tayo dito sa ng 2, we have 0. Hanapin naman natin yung elements na less than kay 0. Ang element na less than kay 0 ay wala. Then, hanapin naman natin ang elements na greater than kay 0. Ang elements na greater than kay 0 ay C1. Kaya rearrange naman natin. Lagay natin C0 kasi walang element. Then, ilagay natin ang greater than kay 0, we have 1. Then, i-copy natin 2, 8, 3, 7, and 10. Dahil sa tamang lalagyan na si 2 at si 0, maghahanap naman tayo ng pivot. At paghanap natin ng pivot, dito tayo maghahanap sa right side. Dahil ang last natin number is we have a 10. Dahil si 10 ang ating pivot, hanapin naman natin ang element na less than kay 10. Ang element na less than kay 10, we have 8, 3, 7. Hanapin naman natin ang element na greater than kay 10. Ang element na greater than kay 10 ay 0. At i-rearrange naman natin, i-copy lang natin, 0, 1, 2. Rearrange naman natin, dahil si 10, parang same lang, 8, 3, 7, and 10. Same lang, nalagay lang si 10 sa tamang nalagyan niya. I-stand natin dito kasi tapos na sila. Then, hahanapin naman natin. Sulat muna natin. 8, 3, 7, and 10. Hanapin naman natin ang 10 dahil tapos na si 10, 2, 1, and 0. Maghahanap naman tayo ng pivot. Dahil ang last number ay yun ang pivot. Kaya ang ating last number ay 7. Hanapin naman natin ang element na less than kay 7. Ang element na less than kay 7 ay C3. Then, hahanapin naman natin ang elements na greater than K7. Ang elements na greater than K7 ay si 8. Kaya, i-rearrange naman natin. We have, copy muna natin, 0, 1, 2. I-rearrange natin. Ang less than, tapos ilagay natin dito ang less than K7. Ang less than K7 ay si 3. Then, ipagitna natin sa 7. Then, lagay naman natin ang greater than K7. We have 8. Then, copy natin yung 10. At, dahil ito na ang n, nasa tamang order na sila. Naka-arrange na silang lahat. Ito ang example ng GRACIA.
6. Heap sort.
Let's start with some terminology. A heap is simply an ordered binary tree. A max heap has a restriction that the value of the parent nodes are greater than the value of the child nodes. Here's an example of a max heap. We'll make use of a few functions when running heap sort. First, we have build max heap. This creates a max heap from an unsorted array. We'll also use heapify. This is similar to build max heap, except faster because we assume part of the array is already sorted. You'll see what I mean. One note, for this video, I'm less concerned with you knowing how these methods work, but rather that they exist and when to use them. Once you understand the basics of heap sort, you'll understand these functions from their pseudocode. Let's get started. We have the following array that we're tasked to sort. In a nutshell, we'll continuously create max heaps to find the largest item. We'll then remove that item from the heap and into a sorted partition. We'll begin by representing our array as a tree. To see how we did that, simply look at the array from left to right and the tree from top to bottom. Now that we have a tree, let's create our first heap. We assume this is an unsorted array, so we call build max heap. Now that we have our max heap, we know the largest item, 9. We swap 9 with the item at the end of the array, 1. Finally, we remove 9 from the tree and consider it sorted. Looks good so far, except we're back to having a tree and not a heap. This time we call heapify, since only the item 1 is out of place. 1 floats down to the bottom, and the largest number heads to the top. We're back to having a max heap. Let's swap the largest number 8 with the item at the end of the unsorted part of the array, 2. We remove 8 and consider it sorted. Again, we need our heap back, so let's call heapify. I think you see the pattern. I'll let you watch the rest of the video without voiceover. We're all done. Our array is fully sorted.
7. Radix sort.
Here's an introduction to radix sort. As an example, let's say we want to sort this array of 6 integers each integer value ranging from 0 through 999, and we want to sort this array in an ascending order so that the smallest number comes first. The first step that we need to take in radix sort is sorting the given array using counting sort, and the keys that we're going to use for that will be the last digit in each number. So it's as if using counting sort to sort an array with the values 3, 9, 0, 6, 3, and 3 in this particular case. And with that, the value that we have with the smallest key, which is 0 in this particular case, will be the first element in the sorted array. And after that, there will be values with the second smallest key, which is 3. So 53 will be the second element. And after that, 633 and 233. And we're going to keep going like that until the very end. And the key thing to remember here is that counting sort is a stable sorting algorithm. And so the values with the same keys, in this example, 53, 633, and 233, they appear in exactly the same order in the sorted array as they do in the original array. And it's really important to use a stable sorting algorithm as a subroutine for radix sort, because if we used an algorithm that's not stable, it just wouldn't work. Now the second step in radix sort is sorting this new array using counting sort again, with the second last digit in each number as the key this time. Once we do that, the new sorted array will look like this. And we're going to repeat the same procedure with this new array. And this time we're going to use the first digit as the key, and you'll notice that there are some numbers without any number in that place, so we'll just use 0 as the key for those numbers. Once that's done, the whole array is going to be sorted. Let's now think about the time complexity of radix sort. First, we're going to define some variables. Let's call the number of elements in the array, or the length of the array, n, and it's equal to 6 in this particular case because we have 6 elements. And let's call the number of digits that we need to represent each number d, and we need 3 digits here. And to represent each number, we're using the base 10 system here. And let's call that b. So b is equal to 10 in this particular case. Now remember that in each step of radix sort, we sort the array using counting sort, using one of the digits as the key. And the time complexity for counting sort is big O of n plus k, where k is the range of keys that we have for each number. And the range of keys in this particular case is 10, or b, because the key ranges from 0 through 9 and it's always an integer. And so each of these steps takes big O of n plus b in time. And we need to repeat this procedure 3 times in this particular case, or d times in general. So the time complexity for the whole algorithm of radix sort will be big O of d times n plus b. And this is quite fast when the range of input is fairly limited compared to the number of elements that we have in the array. And in that situation, depending on the size and the nature of the input, it can perform better than an optimal comparison-based sorting algorithm such as quicksort or merge sort, which would take big O of n log n in time. And one last thing to note here is that there's a range of values that we can choose from for the value of b. We chose base 10 just for simplicity and just to show an example, but we could have chosen, for example, base 100, base 2, 4, 8, or any other positive integer for that matter. And this choice will essentially come down to making a trade-off between time and space, because the larger value that we choose for b, the more space is required for the counting sort step. But at the same time, a larger b or larger base will imply a smaller d, or less number of digits for each number, so it'll take less time to sort the array using radix sort, as long as b is less than n.
8. Counting sort.
To counting sort, let's just say as an example, we're trying to sort this array into an ascending order. And counting sort works the best when the range of numbers each value could have is very small in the array. So let's just say the range of values that we could have for each item is 0, 1, 2, and 3. The first part of applying counting sort is going to be finding the starting index for each number. And it's going to be clear what I mean by that in a second. And the first step for doing that is going to be counting the number of occurrences for each number in the array. So for this example, there's only one occurrence of 0 and 3 occurrences of 1. So I'm going to write down 1 and 3, and then 2 occurrences of 3 and 0 occurrences of 2. And we can store these numbers in an array of length 4 in this particular case. Once we have these numbers, the number of occurrences for each number, the second step is going to be adding each number to the right of it accumulatively. What I mean by that is the first number at index 0 stays the same, and the second number will be 1 plus 3 equals 4, and the third number will be 4 plus 0, which is equal to 4, and the fourth number at the index 3 will be 4 plus 2, which is equal to 6. After that step, we have the numbers 1, 4, 4, 6 for the numbers 0, 1, 2, and 3. The next step is going to be shifting this whole array to the right by one cell. And we're going to do that by looking at this array from right to left. We're going to first start with the last index, which is index 3 in this particular case. And the value there should be the value that's currently in index 2. So we're going to put 4 at index 3. And we're going to do the same thing for index 2. The value here should be what's in index 1 currently. So it should also be 4. And at index 1, we're going to put 1. At index 0, we're going to put 0. And these numbers, 0, 1, 4, 4, are actually the starting indexes for the range of numbers we have in this particular case, 0, 1, 2, and 3. And here's one way to think about it. If you look at the number 3, or the index 3, the corresponding number, the corresponding starting index is 4. And that's because when we sort this array, the number 3 will start at the index 4. Another way to think about it is that there are 4 items that should appear before the number 3 in the sorted array. And that should be obvious if you just look at the first array that we constructed. There's 1 occurrence of 0, 3 occurrences of 1, and 0 occurrences of 2. So adding them up, there are 4 items that should appear before the number 3. And that's why the starting index for the number 3 is 4. Once we have the starting index for each number, the rest is relatively easy. We're going to first initialize a new array that's the same length as the original array, so length 6 in this particular case. And then we're going to iterate through the original array one by one. When we're looking at the first element of this array, which is 1, we're going to check what the starting index should be for this number from the array that we constructed. We see that the starting index is 1, so we're going to put this number into index 1 of the new array. And then we're going to increment our starting index by 1, and it becomes 2. And this is so that when we look at the second instance of the number 1, we'll know that it should go into the index 2 instead of 1. And then we're going to increment it again. We'll do the same thing for each number of this array from left to right until we get to the last number in the original array. Now, you might have noticed that this process makes counting sort a stable sorting algorithm. What that means is that, of course, if you look at different instances of the same value, for example, the number 1, the order in which they appear in the new sorted array is exactly the same as the order in which they appear in the original array. This wouldn't matter if they were just number 1, but if they represented underlying meanings to them. For example, if they were ages of people, 3 different people, let's say Emily, Tom, and George, then we might care if they appear in the same order or in a different order in the sorted array as the original unsorted array. Now let's quickly go through a few important properties of counting sort. First of all, as I mentioned, it's a stable sorting algorithm. And the time complexity for this algorithm is big O of n plus k, where n is the number of items that we have in the original array, and k is the range of numbers that we could have for each item in the array. And finally, the auxiliary space complexity is big O of n plus k for counting sort, because we need to create an entirely new array with length n, the same size as the original array, as well as an array of length k to keep track of the starting index for each number.
9. Bucket sort. Ten shall sort. 11.tim sort. Cocktail shaker sort.
Okay, in cocktail sort, it's a refinement of the bubble sort. Now you just process the whole array and identify the maximum value. So maximum value is what? So maximum value is what? 12, and keep the maximum value right side. That means 9, 7, 2, 5, 4, 1, 3, 12. Okay, now from this place, now check data from right side to left side and identify the minimum value. Okay, now minimum value is 1. So after that the content of the sorting array will be 1. Okay, 7, 2, 5, 4, 9, 3. Now check data from left to right, identify the maximum one. So the maximum one is what? 9. That means identify the maximum one and the content will be like this. Now move from right to left and check the minimum one. So minimum one is what? 2 is the minimum one. So 1, 2, 7, 5, 4, 3, 9, 12. Now check this particular part only, identify the maximum value, and so the output will be 1, 2, 3, 5, 4, 7, 9, 12. Now check this one, identify the minimum value. So 3 is the minimum value. So 1, 2, 3, 5, 4. Now check this one, identify the maximum value and get the final answer. So 1, 2, 3, 4, 5, 7, 9, 12. Okay, so this is nothing but our cocktail sort. So that means process data from left to right, okay, and identify the maximum value. So maximum value is 12, swap with this 12. So the output will be 9, 7, 2, 5, 4, 1, 3. So swap these two data, swap these two data, 3 and 12. Now this is the sorted part, unsorted part. Now check from right to left, identify the minimum one. So the minimum one is what? 1. Then swap 1 with 1. Then swap 1 with 9. So 1 will be here, 9 will be here. Now the unsorted, this is the unsorted part, and these two part the sorted part. Now check the whole data, identify the maximum one. So maximum is what? 9. So swap 9 and 3. So 7, 2, 5, 4, 3, 9, 12. Now this is the sorted part and unsorted part. Now identify the minimum one. So 3 to 7, the minimum is what? 2, and swap these two. So 2 and 7. So this particular part is the sorted part, this particular part is the sorted part, this particular part is the unsorted part. Now 7, 5, 4, 3. So 3, 5, 4. Identify the maximum one. So maximum is what? 7. So swap
13. Pigeonhole sort. Cycle sort.
We will see an application of cycle sort with Uno cards and OK stones. Here, Uno cards will represent our indexes and OK stones will represent our elements. We start our sorting with our first element. As you can see, it is 4 in here. When we look at the right side of 4, we can see that there are 3 elements that are less than 4. So we need to increase the index of 4 by 3 and replace it with the element at that index. Now we have 6 at 0 index. Similarly, since there are 5 elements less than 6, we increase its index by 5 and replace it with the element at that index. Since there is no element to the right of 1 that is less than it, we leave it in place and the first cycle is completed. The elements of the first cycle are 1, 4 and 6. We will now look at the element in the first index. Since there is no element to the right of 2 that is less than it, we increase its index by 0 and it stays in the same place. We keep doing the same thing for the remaining ones, such that 5 and 3 will swap and that will be our second cycle. We see that 1s up to 6 are sorted and in the right place. There is one element less than 8 to the right of it, so we increase its index by 1 and swap places. Thus, we complete our sorting with 3 cycles, and the array is now sorted.
15. Comb sort.
Comb sort is a descendant of bubble sort. Instead of checking every 2 adjacent members, it uses something known as a gap and a shrinking factor. It compares the elements which stand at the indexes separated by the gap, and swaps them if an inversion exists. It consistently lowers the gap by using this shrinkage factor until it descends into a normal bubble sort. It pales in comparison to the algorithms which have yet to come, but is still a fundamental concept to grasp and understand. We start by initializing the gap with the size of the array. We assign 1.3 as our shrinking factor, or otherwise the algorithm will make 2 inconsistent jumps. The swap boolean will be used for our main escape condition of the cycle. We reassign a new value to the gap at the beginning of every major iteration. We will have a condition for making swap false only when the gap value is too low. Also, if the gap value goes below 1, we must assure ourselves that it will still become 1 so we can resort to our basic bubble sort. We always start iterating from the beginning of the array, and make sure that it doesn't escape the boundaries. We also have to always make our swap true when inversions are present, so even when the gap is equal to 1, we can restart our main loop.
And now we have an example of stub short. We have initial list, we have 9, 6, 3, 1, and 7. Sa stub short daw, ang first na elements and last elements is i-compare daw natin yan. Dahil greater than ang first na element and less than ang last na element, iswap natin yan. Swap natin ang 7, tapos copy natin ang 3 and 1. Then, lagay natin dito ang first na element. Sa step 2 naman, step 2. Ang step 2 daw is the short first 2 over 2, 2. Ang first 3 elements daw, ang ating first 3 elements naman daw ang ating sublist. We have first 3 elements, we have a 7, we have a 6, and we have a 3. I-compare naman natin yung first na element and last element. Compare natin siya. Since ang 7 is greater than sa 3 and 3 is less than sa 7, i-swap natin yan. Swap natin, we have 3, 6, and 7. Sa step 3 naman, 3. Ang step 3 daw is short last 2 over 3. Ang last 3 elements daw, ay kuha naman tayo ng sublist sa last 3 elements. We have a sublist, we have a 6. Ito ang sublist. We have a 6, 3, and 1. I-compare naman ulit natin yung first na element at last na element. We have 6 and 1. Dahil greater than ang 6 sa 1 and less than naman ang 1 sa 6, iswap naman natin yan. We have 1, 3, and 6. And then, ang ating sublist is magiging, sublist natin becomes 3, 7, 1. And then, 3, 6. Ang sublist natin becomes 3, 7, 1, 3, and 6. Sa step 4 naman natin, step 4, short first 2 and 2 over 3 again. Kukuha naman daw tayo ng first 3 elements. Ang ating first 3 elements dito, we have a 3, 7, and 1. I-compare naman natin ulit yung first na elements at last na element dito. We have 3 and 1. Dahil greater than ang 3 sa 1 and less than ang 1 sa 3, isuswap natin yan. We have 1, 7, and 3. And then, repeat lang natin yan to recursively until fully shorted. Then, repeat. After shorting through this recursive step, the final shorted list becomes ganito. The final shorted list become 1, 3, 6, 7, and 9. Ito na ang ating final shorted list sa stub short. At yan ang example ng ating stub short.
17 gnome sort.
Gnome sort is kinda a legitimate child of insertion sort and bubble sort. It behaves like insertion sort in its sorting approach, but compares and swaps adjacent items like bubble sort. Interestingly, it works with a single loop but has a quadratic time complexity. We have a video for insertion sort and another one for bubble sort. If you're interested, here are the links. But for now, let's see how gnome sort works and what is its time complexity. The idea is comparing two adjacent items. If they are in the correct order, it goes one step forward. If not, it swaps them and goes one step backwards. It's plain to see that it might compare two items multiple times. No wonder why it was originally named a stupid sort. It continues doing that until it cannot go any step further, and that's when we can be sure that the array is fully sorted. Without wasting time, let's jump into the code. But before that, please like this video if you think it's useful and informative, and consider subscribing to the channel. The algorithm is simple. We define a variable to keep track of where we are in the array and do the following steps over and over, while the defined variable is less than the size of the array. If we are at the first element, or if two adjacent items are in the correct order, go one step forward. Otherwise, swap the items as they are in a wrong order and go one step backwards. Clearly, the algorithm doesn't contain any nested loops, so at the first glance, it might seem it's in an order of n. But that's not true, as we might go backwards in the array as well. Let's count the number of comparisons when the input is already sorted, and when it's sorted in reverse order. The best case is when the input is already sorted, so the number of comparisons is in an order of n. However, when it's reversely sorted, the number of comparisons grows much faster. Indeed, gnome sort has the worst case and the average case of n squared, and in practice, it's even slower than insertion sort. Thank you for watching the video.
18 bitonic sort. For
And now
example,
we have a bitonic sort. Example, we have 3, 7, 4, 8, 6, 2, 1, and 5. Step 1, step by step natin. Okay. Step 1, divide into bitonic sequence. Divide na natin into bitonic sequence. Divide natin. Divide natin ito. 1, 2, 3, 4, 5, 6, 7, 8. 8. Divide natin into bitonic sequence. We have 3, 7, 4, 8, 6, 2, 1, and 5. Divide natin into bitonic sequence. Yan. Na-divide na natin into bitonic sequence. And then, split the less into two halves. Split down natin yung less into two halves. We have 3, 7, 4, 8. This is called ascending. And we have a 6, 2, 1, and 5. This is called descending. Okay. And then, short each half. Short down natin each half. We have a 3, half. Dito daw na side, we have less than to greater than. Lagay natin dito, we have less than to greater than. We have 3, next 4, next 7, and next 8. And then, dito naman sa kabila, ang descending, gagawin po natin greater than to less than. We have 6. We have a 6. We have a 5 and 2 and 1. Yan ang tinatawag na short each half. Dito, less than to greater than, and dito naman sa kabila is greater than to less than. Step 2. Sa step 2 naman natin is create bitonic sequence. Create naman natin yung bitonic sequence. Sequence niya. We have 3, 4, 7, 8, then 6, 5, 2, and 1. Dahil na-create na natin ang bitonic sequence niya, gagawa naman natin ang step 3. Gawin natin yung step 3. Ang step 3 daw is bitonic merge. Recursively compare and swap elements to the merge into a sorting sequence. Recursively daw natin and recursively compare and swap na natin yung element to merge into a shortened sequence. Example, ito daw. Recursively, lagatan muna natin 8, 6, 5, 2, and 1. I-compare na natin and compare daw natin. Dito natin i-compare yung dinivide natin kanina. Itong 3, compare natin dito sa 6, 4, compare natin dito sa 5, 7, compare natin itong sa 2, and 8, compare natin dito sa 1. And then, sabi dito, and swap element to merge into a shorted sequence. I-swap na natin yung element, compare and swap element into a shorted sequence. Itong 3, kinumpare natin sa 8, ay sa 6. Mas less than pa ang 3 sa 6? Yes, mas less than. Kaya, i-stay lang natin dyan. Itong 4, mas less than ba ang 4 sa 5? Yes, mas less than ang 4 sa 5, kaya stay natin dyan. 7, i-compare natin sa 2. Ang 7 ba is less than 2? No, kaya i-swap natin yan. Dito natin ilagay ang 2. Then, ang 8, less than ba ang 8 sa 1? No, kaya ilagay natin dito ang 1. Copy natin yung 6, 5, at ilagay natin dito ang 7 and 8. And then, pagkatapos natin swap elements to merge into a certain sequence, short each half recursively until fully shorted. I-short na natin ang and each half recursively until ma-fully shorted natin. Kumbaga, ilagay na natin ito sa order ay sa right order niya. Lagay na natin dito si 1, then sunod si 2, then sunod si 3, then si 4, then ang sunod sa 4 is si 5, then si 6, si 7 at si 8. Yan ang ating final result. Yan ang example ng bitonic sort.
19. Tournament sort.
Hey guys, just wanted to make a video to explain my tournament sort. It's kind of confusing probably reading it, so hopefully this will help. So we have the data set that he gave us right here. This is kind of what the example look will be, and here is how we start. So as you can see, I put 8 and 2 together and I have 9 and 5 grouped together. So you want to compare these and move them up. So for instance, this one would be 2 and this one would be 5. These would technically go blank, and you would replace them with the next numbers in line. So 6 and 1 would be the next 2. So this one would be 6, this one would be 1. And then when you get here, you want to compare these two first. So 6 is not going to be less than 2, so we leave it. 1 is less than 5, so we switch them. So this goes back to being 5, and this will go to 1. Now that we have nothing that we can compare as far as being less than terms for our minimum, we're going to do 1 and 2. So this makes the top of the tree. So we have 1. And then this goes empty. And then now you compare 9 and 5 because this is an empty set. So here we have 5. That goes empty. And because we have nothing else to compare, we output. So our first output would be 1. That leaves this empty again. And then we compare 2 and 5. Well, 2 would move up. And we compare 8 and 6. This becomes 6. Nothing to compare after that, so we output 2. Makes it go empty. And now we compare 6 and 5. Well, 5 moves up. We mark that one out. And we move the 9 up. And nothing to compare right now, so we output 5. And we do the same thing. We just repetition over and over again. 6 moves up. Mark it out. The 8 moves up. And output 6. And then we compare 8 and 9. Well, 8 moves up, and as you can see, it just goes in order. So once you mark that out, put 8. Well, you can't compare anything, so 8's outputted. Then the same thing with 9. And that gives you your minimum sequence from least to greatest.
BOGO sort.
BOGO sort is a ridiculous and impractical sorting technique that repeatedly shuffles the array of elements in a random order and then checks to ascertain if the resulting sequence is sorted. This process is iterated indefinitely until the array is found to be in the correct sorted order. Due to its reliance on sheer luck for sorting, the algorithm's performance is extraordinarily poor. The number of possible permutations of the elements is n factorial. Thus, the time complexity is big O of n.
And now you know how to work the 20 different sorting technique. By the way, I am your Miss K. DELA. I hope you enjoy my video. Thank you for watching.